What's up, Zan?
What's going on, Jay? Hey, Jay, what do you think of my new socks?
They're okay. What else did you waste your money on?
Jay, what are you talking about? Everybody's wearing these. It's the new trend.
Yeah, whatever. While we're on the topic with trends, do you mind helping me out with the periodic trends?
But I think we're going to need to go to the blackboard. So, Jay, when we're talking about periodic trends, like electronegativity, ionization energy, electron affinity, and atomic radii, it's important to take into consideration effective nuclear charge. Now, you're going to ask me, Jay, what's effective nuclear charge? Well, it is the force exerted by the nucleus on the outermost electrons of an atom.
Oh, the outermost electrons, the valence electrons, right? So why is this charge effective?
So it's effective, Jay, because it is the net force experienced when we take into account the shielding effects of electrons between the nucleus and our outermost electrons.
Oh, okay, that makes sense. So the positively charged nucleus wants to pull in the outermost electrons, but the electrons in between get in the way.
Precisely, Jay. There's actually a mathematical way we can write effective nuclear charge that you could use on the MCAT. So it's going to be your effective nuclear charge is equal to Z minus S, where your effective nuclear charge is equal to the atomic number minus the shielding electrons. So Jay, why don't you calculate the effective nuclear charge for sodium and magnesium?
Yeah, sure. All right, so first we got sodium, which I know is an alkali metal, so it's going to be one valence electron. So its effective nuclear charge is going to be its proton number, which is 11, minus all the non-valence electrons. So it has to be 10 because it has 11 protons. 11 out of those 11 electrons that it has, 10 of those must be non-valence, considering that it only has one valence electron. So 11 minus 10, we got positive 1. Now, magnesium, an alkaline earth metal, has 2 valence electrons. So if you look at its effective nuclear charge, we're going to look at its proton number, 12, minus all the non-shielding electrons. I know it has 2 valence electrons, so 10 of those must be non-valence for shielding. So magnesium has a positive 2.
So Jay, what do you notice about the effective nuclear charge trend as we go from left to right?
So Zan, is it correct to say that since my effective nuclear charge is going up as I go to the right, that my atomic radius goes down? Because when I approach atoms like, say, fluorine, the effective nuclear charge is so high that the outermost electrons are pulled in more?
That's exactly right, Jay. So for the MCAT, there are really 4 major trends that you need to know about: atomic radius, electronegativity, ionization energy, and electron affinity. So for atomic radii, it's the distance from the nucleus to the outermost electrons. And as your effective nuclear charge increases, your atomic radii is going to decrease because you're pulling those electrons in your outermost shell closer towards the nucleus, really shrinking the size of your atom. Now for electronegativity, it's a tendency for an atom to attract a bonding pair of electrons towards it. Now, for electronegativity, for example, if you have oxygen and hydrogen in a bond, because oxygen has that higher effective nuclear charge, it's going to pull those electrons. It's already pulling it closer to its nucleus, and that's why it's a more electronegative element. Now, for ionization energy, it's the energy needed to remove the outermost electrons from an atom in the gaseous state. Now, because, and how it's related to effective nuclear charge is that atoms with higher effective nuclear charge are going to have higher ionization energies to remove those electrons, because they're pulling, it's such a strong pulling force from the nucleus. So to remove those electrons, it's going to require more energy, and that's why ionization energy increases with atoms that have higher effective nuclear charge. And finally, the last trend, electron affinity, it's the energy released when an electron is added to an atom in its gaseous state. Now, for electron affinity, it increases with effective nuclear charge. And the reason for that is that effective nuclear charge is the pulling force of electrons towards the nucleus. And we can think of electron affinity as how badly does an atom want electrons. So with higher electron affinity, it correlates with higher effective nuclear charge.
All right, Zan, that makes sense. So basically, as I'm going to the right, my electron affinity is going to go up. My electronegativity is also going to go up. My ionization energy is also going to go up. And the only thing that goes down is my atomic radius, right?
Exactly, Jay. So let's talk about what's going to happen when we go down the periodic table. Well, as we go down, we're going to be adding energy subshells. So you can kind of think of it like an onion with all the layers branching out from its center core. And as we increase these number of layers, we're increasing our distance from the center nucleus. And if you remember from physics, Coulomb's law is the force is equal to a constant times Q1, our first charge, Q2, our second charge, over r squared, our distance. So our distance is increasing from the central nucleus as we go down a group, so our force is also decreasing. Now this has consequences on all of our periodic trends. For radii, for atomic radii, we're going to increase as we go down a periodic table, because that force of pulling from the outermost electrons has decreased. So they're going to spread out more and kind of branch out. Those electrons are going to, be more free and, extend their range from the nucleus. Now for our three other trends, electron affinity, ionization energy, and electronegativity, they are all going to decrease going down the periodic table and going down a group, because this force from the central nucleus has decreased.